All right, so welcome everybody to round 2 of the Algebra, Particles, and Quantum Theory seminar series. I'm pleased to introduce you tonight's speaker, John Huerta. John is a mathematical physicist currently at the University of Lisbon. He received his PhD in mathematics at the University of California, Riverside. John next went on to postdoctoral positions at the Australian National University, then at University of Lisbon, where he was subsequently promoted to research scientist. John's research interests may be summarized succinctly as differential geometry and higher structures. He has worked on topics like bundle gerbes and supermanifolds, how spacetime emerges from a superpoint, and has written a series of papers under the title of Division Algebras and Supersymmetry. As you'll see for yourself, John is not only an expert in algebra and geometry, but also an exquisitely clear speaker. Tonight, he will be telling us about a paper that he and John Bias wrote called The Algebra of Grand Unified Theories. The Algebra of Grand Unified Theories is an article that won the Levi L. Conant Prize for Best Expository Paper. It is also one of my all-time favorite articles that I recommend everyone working in particle physics read. Now, before we begin, I would like to emphasize that everybody who showed up here today is here to learn. And so I hope that everyone feels comfortable enough to raise their hand and ask a question throughout the talk if they have one. If you accidentally ask a silly question, it is not a big deal. You just brush yourself off and try again next time. I would especially like to encourage questions from graduate students, upper level undergraduates, and postdocs. So John, anytime you're ready.
Thanks, Cohl. I really hope that I can live up to that claim that I'm a crystal clear speaker today, because I'm not really satisfied with my talk yet, but you know, sometimes these things happen. So to start off, I wanted to start in a very simple place. Since this is the Algebra, Particles, and Quantum Theory seminar, I wanted to talk about the question, what is an elementary particle? So any definition that I can give, I'm a mathematician, so I want to give definitions. That's part of the culture of mathematics. But since I'm trying to define something that really exists out in the real world, this definition is going to be provisional. But there are pretty good definitions. And I wanted to give two versions of a definition for an elementary particle. And my first definition is going to be that it is a quantum system. I'm taking for granted that reality is quantum, where if you know all the charges, I'm using charge in a very general way here that I'm going to explain in a minute. If you know all the charges, you know everything. So another way to rephrase this would be that it's a quantum system that is completely determined by its charges. And by here, I'm including things like mass and spin, even though those are not usually considered charges. I'm just considering like these physical attributes of particles that are invariants of the particle, and we think of them as sort of defining which particle we're looking at. And I want to give the mathematical definition that probably goes back to Wigner. We'll see that a lot of the material in this talk is kind of based on the mathematical work of Wigner, although I wasn't quite able to trace it back to its origin, which is that an elementary particle is an irreducible representation of the symmetry group of physics. And I want to, I want to argue, I want to use this talk as an opportunity to try to convince you that these two definitions are really the same. So let's get started with that. And I will tell you what an irreducible representation is in a moment. But first, I want to give you the punchline of the talk right away, which is, how can these two definitions be the same? So the answer, coming from physics, so the it's not really fair to call this an answer. It's more that there's an analogy here that's going to get more apparent as I write this out. So in physics, we analyze quantum systems by finding a complete set of commuting observables. And once we have this complete set, we then diagonalize them by finding a basis of eigenstates. Are there any questions about this procedure in quantum mechanics?
I think most people would probably understand.
Good. I was hoping
Yeah.
I was hoping for that, since this is a physics seminar.
Yeah.
But so here's the thing that many people may not be familiar with.
Andre has a question here. Do you mind if I'll unmute?
Please, Andre.
Just 1 second here. Just 1 second. There we go.
Hey, why do you only consider, commuting observables? It's perfectly fine usually to have also quantum numbers in non-commuting observables. You cannot determine them in parallel, but why not?
Yes. So that's why I only consider commuting observables, because I want to know the quantum numbers that I can determine simultaneously.
But you included spin. For spin, this already is.
Sorry?
But you included spin in your definition of the particle, and then you would have to throw it out here because.
No, I won't. I'll show you why. That's kind of coming up in the next answer. So in mathematics, there's a very analogous thing that people do, specifically in Lie theory, the mathematics of the representations of Lie groups, which is really our topic today. We analyze a representation by choosing a maximal torus and diagonalizing. Its action. So while it's true that the different axes of spin observables don't commute with each other, I'm going to choose a favorite one. We usually call it the z-axis spin, or maybe like sigma z for that Pauli matrix, and I'm going to analyze the spin of the system using that. And that corresponds to what mathematicians call choosing a maximal torus of SU2. And I could have chosen any direction, of course, but if I choose one, then I can use it.
Which means your choice will not be unique, right?
Yeah, the choice is not unique, but they're all related. They're all conjugate inside of the group, which you could think of physically as saying that they're all related to, say, changing the orientation of my measurement apparatus. Any other questions? Okay, I'm going to move on. So now I'd like to give some definitions. Some honest mathematical definitions. So since these are about mathematical objects, they do have definitions. That's how mathematical objects are created. They're created by definitions.
We've got a couple more questions, John. If you don't, are you ready?
I absolutely don't mind.
Very good. Okay. Go ahead, Andres.
Oh, okay. Just because you said they're conjugate in the group, I'm not sure about that, because you may have some that don't commute and they're not conjugate in the group, but just without the automorphisms. So you say you can change the, rotate the apparatus, but if you think of CP or something, you may not be able to flip matter and antimatter in your lab.
Yeah, that's true. If you're outside of a connected group, then there may be you may have to do something else. But I'm thinking specifically about spin, which is described by a representation of SU2, and SU2 is connected, and its maximal tori are all conjugate within the group.
Yeah, agree with that.
Anything else?
So Yanis has a question. Go ahead.
Yes, my question is more rudimentary. Why did you call the first choice a physics and not a mathematics question? I think it's more like a functional analysis approach and versus a more geometrical approach, but both are mathematics, right? And I think mathematicians devised the first approach that we call physics. Is that
about how to analyze a quantum system?
Yes.
Yeah, I was trying to figure out who first came up with this idea. I mean, like, I was introduced to this idea in a physics textbook for quantum mechanics. So that's partially why I think of it as a physical idea. But I was briefly trying to figure out who originally proposed it. And it's possible it was someone like von Neumann.
Right. That's what I would think.
Yeah. Also, you find it in Dirac's textbook on quantum mechanics, for example. Like, it's whoever first came up with it, it became very, very widely adopted.
Okay.
I would be interested to know who first came up with it.
I think both of them were. I think Dirac, we think of him as a physicist, but I think he was a mathematician for the most part. I think. But that's semantics.
Yeah. Anything else? Okay. So what's an irreducible representation? First, let me say what a representation is. This is a typo here. This should say a representation. V of a Lie group G is a group homomorphism from the group into the general linear group. So in other words, I can turn elements of G, some abstract group, or maybe abstract group, into matrices, invertible matrices that act on V. And if I compose two such matrices, they came from the corresponding element, the corresponding composite in G. It's irreducible if whenever I try to write it as a direct sum, this attempt fails. And I end up just with one of the direct summands is all of V, and the other one is 0, or vice versa. So another way to phrase this condition might be V is not the direct sum of U plus W for any non-trivial U and W. And it's unitary if V is a Hilbert space and all of those matrices that came from the representation turned out to be unitary matrices, unitary operators on this Hilbert space. And since we're thinking about quantum systems, we should probably be thinking about unitary representations. But here's a proposition. Any unitary representation V of G decomposes into a direct sum of irreducible representation, irreps. So I could think of V as splitting apart into U1 plus U2 plus U3, etc. And if it's finite dimensional, this has to stop eventually. If it's not, it could be really big. And most of the representations we'll be talking about will be finite dimensional. So why should we be talking about unitary representations? Well, like I said, a lot of the basis of this talk is due to work of Wigner. And here is Eugene Wigner. And he has a theorem that was talked about earlier in this series this year by John Baez called Wigner's theorem, which is that symmetries of a quantum system with a Hilbert space H are given by unitary or anti-unitary operators on H. And that means that we can, so we could think about representations that include anti-unitary operators. But really, this means that I'm going to focus on those representations that are unitary. Can anyone guess why I'm going to focus on these?
Go ahead.
conservation of probabilities. Probably, my point is physical, not mathematical.
Well, the thing is that the anti-unitary operators still conserve probabilities. That's part of Wigner's result. So that's not actually the reason. The reason is that for us, it'd be interesting to consider alternatives. There are always all of these alternatives, and as a mathematician, I don't know all of the physical reasons that they've been ruled out, or even if they have been ruled out. But for us, G is connected. And if you think about the groups of unitary or anti-unitary operators on V, that's disconnected, right? There's no path connecting unitaries to anti-unitaries. So because G is connected, it can only go to the unitary part. So that's a very mathematical explanation for why I'm going to consider only the unitary ones. But I haven't given you a physical explanation for why I'm going to consider only G connected, and I'm not sure that I know one. But there is a disconnected group coming up here. So there's a famous theorem due to Coleman and Mandela. Here's Sidney Coleman on the left and his PhD student, Jeffrey Mandula, on the right, that the symmetry group of a quantum system described by an S matrix, so this is a very general kind of theory, has to be, and satisfying certain assumptions, of course. Theorems always have hypotheses. The S matrix, I thought, was the key hypothesis, so I actually spelled it out. But there are other various somewhat technical hypotheses. But the symmetry group of such a quantum system has to be the direct product of the Poincare group, the symmetries of spacetime, and another group, which we're going to call the gauge group. And this allows us to start getting our hands on these irreducible representations described by the symmetry group of physics, because it tells us more or less what the symmetry group of physics is. It's the Poincare group times some other group. And here are these groups spelled out. It's another typo. Poincare group consists of all rotations, reflections, Lorentz boosts, as well as other symmetries that I'm sure people would be more or less happy if I called them parity, time reversal, and the product of parity and time reversal. So this part, the Lorentz group part, is there, but also there's the translation part. And besides the Poincare group, which we know is there, thanks to Einstein's special relativity, we have the gauge group. And this was something of a puzzle. This is something that had to be figured out. So, and in some sense, it's still a puzzle, which is the topic of today's talk. But for the standard model, at least, which I will start by introducing. The gauge group G is, well, it's a Lie group. And for the standard model, it's the Lie group U1, which is just the group of phases, just the group of complex phases, times SU2, which we're familiar with from spin, times SU3, which is just 3 by 3 special unitary matrices of determinant 1, not too different from SU2. And so what I've been asked to do by my mathematical definition of elementary particles is, if I want to find elementary particles, I need to analyze the irreducible representations of this product of groups. So I want to determine irreps of the Poincare group across the gauge group. And first we'll talk about the standard model gauge group. But
Howard,
yeah.
yeah, I can let you finish your sentence.
First,
Howard.
we'll talk about the standard model gauge group, but then we'll talk about some more general ones.
Okay, so Howard has a question here. Let me unmute you. Go ahead, Howard.
Yes, please.
It was just a quick question.
Yeah.
Oh, sorry. Just a quick question. Does the Coleman-Mandula theorem imply that the gauge group is compact?
That's a really good question, and I don't know the answer.
Okay.
I would love to know the answer.
Thanks.
Sure. All right. So we want to analyze irreps of groups of a group that is the product of two groups. Here's a fact. The irreps of a product of groups, G times H, are tensor products of the irreps, where V is an irrep of G and W is an irrep of H. So if our group is this one, then an irrep has the form V tensor W, where V is an irrep of the Poincare group, and W is an irrep of the standard model group. So oh, and yeah, I should also add that these are unitary irreps.
Howard has
Because, like I said, we're going to have unitary representations.
Okay, so Francis, you've got a question.
Sure.
Go ahead, Francis.
Hello,
Okay.
can you hear me? With every sensor.
I could hear you when you said
wanted
hello.
to
Can you
know
hear me?
If you,
Francis?
yes, I can hear you.
I can't.
Yes, I can hear you.
I can't hear you well. I'm sorry. I can hear you a little bit. Could you maybe type your question?
The chat's not on.
Okay, let me.
Oh, the
With-
chat's not
With a
able. Okay.
reducible tensor representation. Is it better? Is it better? Is it better, please?
It is, yes.
It's better, yes.
Okay. With your tensor product of the Poincare and the gauge,
Yeah.
do you take into consideration the dimensions for the Poincare group and your gauge?
I'm not really considering that, no. But the thing that I was going to say in a minute, well, I was going to say it now, more or less, is that the unitary irreps of the Poincare group are infinite dimensional.
Okay.
Whereas the unitary irreps of the standard model group and the other gauge groups that we're going to talk about, they're all finite dimensional. And that has to do with the fact that the other groups are compact and the Poincare group, these gauge groups are compact, the Poincare group is not.
Okay. Okay. True. Thank you.
Sure. So these irreps, the irreps of the Poincare group, these are described by yet another result to do to Wigner's classification. You get an irrep VMS for M, any non-negative real number, and S, any non-negative half integer. So irreps of the Poincare group are labeled by mass and spin. And this may have been the first hint in physics that we should think of particles as being irreps. But I don't want to think about the irreps of the Poincare group today because they're infinite dimensional, they involve analysis. I want to focus on the irreps of the gauge groups because they're finite dimensional and you can handle them with just algebra.
Yanis has a question here.
Please.
Go ahead.
Yes.
Yanis.
Now, if the representations were anti-unitary, then would the mass then be negative, and that's the reason why we have to take unitary?
So I don't think that right. So what operator determines the mass? I think the operator in Wigner's theorem whose eigenvalue is the mass is basically the time translation operator. And that's so basically the Hamiltonian. And that's sort of always unitary. So I think I think it would not. So if you allow, so you can't have an anti-unit. So yeah, first of all, you can't have a purely anti-unitary representation because groups always have identities, and the identity operator is always unitary. But you can have a representation where you have some unitary stuff as well as some anti-unitary stuff. And I would guess that it's a theorem that you can never have, even if you allow anti-unitary stuff, the time operator, the Hamiltonian operator, can never land in the anti-unitary part. But that's a bit of a guess.
I thought that the energy was the eigenvalue of the energies are the eigenvalues of the Hamiltonian operator, but
Right, and no, but so for a relativistic particle that's not subject to any forces,
they are the same. Okay.
They are the same. All right. So let's talk about how this kind of analysis that I have in mind just for the electromagnetic force. So I'm going to choose an operator. I'm going to choose an observable, Q, and this observable is supposed to give me the electromagnetic charge of whatever particle I encounter. And as we know, the fundamental fermions in the first generation are the electron, its neutrino, the up and down quarks. It's everything we need to make the matter that's around us, and we barely even need the neutrino. The neutrino is obviously necessary for certain decays, but it doesn't form a bound state with anything we know and love. So I want to think of these particles as states in a Hilbert space. And when I act on them by this operator, they're eigenstates for the charge. So the charge of the neutrino is 0, of course. The charge of the up quark is 2/3. The charge of the down quark is -1/3. And so note that in a representation in a Hilbert space where I have electrons, neutrinos, up and down quark states, this charge operator is diagonal. And it tells you specifically which particle you're dealing with. Like all of the particles that we've listed so far have a unique charge. So knowing the charge is enough to identify that particle.
Hillary has a question. 1 second here.
Yeah.
Go ahead, Hillary.
Can you hear me?
Yes.
I got a couple of questions.
Sure.
One, where does the photon fit into this? And 2, why are you including the neutrino when it only interacts through the weak interaction?
That's a good point. I mean, I guess I wanted to point out, I wanted to illustrate how the charge operator acts on a neutral particle. So because the neutrino is neutral and its charge is Q, I wanted to include it for that reason. And also because in just a minute, I'm going to unify the electromagnetic force with the weak force and talk about the weak interaction. What was your other question? Oh, the photon.
Or the photon, yeah.
Yeah, I'm mostly focusing on particles of matter in this talk. That's one of the deficiencies of one of the issues is that I'm not really going to discuss dynamics at all in this talk. This talk is purely what physicists, I guess, call kinematics. And so I can focus on matter without really saying much about how it interacts and therefore having to talk about gauge bosons. But it's just a simplification to narrow our focus. So I guess I wanted to say that you can think of this U1 as being generated by Q. In other words, this is an operator. This Q is a Hermitian operator on some Hilbert space. And I could think of the group that looks like exponential e to the I t q for all t. And that's the U1 of electromagnetism. So this is actually the first example of a torus, except in this case, the torus is the whole group. And why do I call it a torus? Well, mathematicians call it a torus because it's a kind of torus. It's just a circle. It's the one-dimensional torus. In a second, we'll see the two-dimensional torus. So now I'd like to talk about the electroweak force. And so the electroweak force, it's important to understand that this new U1 is not the same as the old U1. So previously for E and M, this is the U1 that's generated by Q. But here, this U1 is going to be generated by some funny other charge, a new operator called the hypercharge. So basically, we want to pick a maximal torus. And here, the maximal torus is going to be two-dimensional. There's going to be this U1, the one U1 that you see right there. And there's going to be another U1. And this U1 is going to be living inside the SU2. It's going to be the U1 that's coming from the isospin. So remember how I said that, when you're thinking about spin, you might pick a particular axis and measure the spin along that axis. So we're going to do the same thing with isospin. And yeah, this will be that kind of U1, where I3 is this following element of SU2. I guess it should be 1/2, -1/2. In other words, really close. Really, well, actually, the same as the matrix as Pauli's third matrix. And now I want to use this maximal torus to describe my particles, the particles that I know. But there's a new wrinkle, which is that the electrons, the particles now come in two varieties. One of the mysteries of the weak force is that it only talks to left-handed particles or right-handed antiparticles. I don't want to introduce antiparticles yet. So it tells us that where we once thought these particles were the same, there are actually two of them. And how do we understand the action of this torus on these particles? Well, there's a formula that relates the charge, the hypercharge, and the weak isospin. And that formula, well, that's a little too premature. I wanted to get to this formula. This is the Gell-Mann-Nishijima formula, which they discovered analyzing strongly interacting particles, but it turns out to be really related to the weak interaction. And it just says that the charge is equal to the isospin plus 1/2 the hypercharge. And using this formula, which I should have put a couple slides earlier, we can take the charges and isospins that we know. We know that the left-handed neutrinos and the left-handed particles will have isospins because they're going to feel the weak interaction. The right-handed particles will not. That's how I've filled in this column. And we already knew the charges. I reviewed that for you on the previous page. And we can now use the Gell-Mann-Nishijima formula. Did I read? Oh my God. There it is. Sorry, I accidentally duplicated a slide. So now we can use the Gell-Mann-Nishijima formula and compute the hypercharge and isospin values.
We've got a question, just one sec here.
Yes, please.
Go ahead, Huey.
Sorry to interrupt. I think I got lost somewhere. I think you mentioned the three charges, and there are Q, which are the 4x4 matrix, and Y is the hypercharge, and the I is the isospin.
Yes.
And you mentioned that you pick up max torus, which is T2 equals U1 times U1.
Yeah, it's U1 times U1. That's right.
Yeah, but you mentioned three charges right before, so.
Right, and the thing is that they are related to each other, so you can use any two of them, and it's better to use the hypercharge and the isospin because the hypercharge really is the hypercharge generator really is this first factor of U1 in the electroweak force. The other one is the isospin by definition. The electromagnetic force, the electromagnetic torus that we just saw on the previous page does fit into this picture, but it fits in a way that's given by the Gell-Mann-Shijima formula, right? The Gell-Mann-Shijima formula says that you have a certain slope, that the Q generator has this slope of like 1/2 in the IY plane. And you can see that you can map that onto the torus by exponentiating it. And you would see that it wraps around the torus. So this is the torus from the previous page, from the electromagnetic interaction. This is the EM torus.
But the dimension of the R3 and the Q are different. Because the dimension of the Q, and when you consider 4 different particles, and they are at the root, they are 4 times 4.
That's so I did write the action of Q on a 4x4 as a 4x4 matrix because of the number of particles I considered. But you see that in fact Q really only cares about 1 particle at a time. So really the irreps of Q are 1-dimensional. And here the same thing is true. I could act on each of these particles by Q or by Y, and I would get some number. So even though this is now like an 8x8 matrix, it's still diagonal in Q or Y.
Okay, thanks.
Okay. So I was going to talk about grand unified theories, and I barely laid out the standard model. So here are these particles, but I've now changed out the charge for the hypercharge because that's more convenient with this torus. And the point that I want to make is that knowing these values is telling me the representations. So here are the representations. These are the electroweak representations of the first generation of fermions. Here you see a number of different representations of U1. And the way that this works is that if you have an element of U1, alpha in U1 acts on Z and CY, this is hypercharged, so I'm going to call it Y, by alpha 3Y times Z. And it acts, and S22 acts on C2 in the obvious way we know and love. let me try to find a stopping point. So, of course,
I would say, as far as time goes, I don't know what your timing is like, but so these, so as far as people in the audience go, if they, have a schedule and really need to go, they can. I don't know what your timing is like, but this is going to be recorded and put online. So if your talk does run over, it's okay, because people who need to miss the last part of it can always just come back and see it. But I don't know if you've got something after this that you also need to go to. But just to let you know that the option is open if you want to run over time. It's that's a possibility.
Okay, let's see how this goes. So, like I said, the gauge group of the standard model is not just this electroweak part. This is the electroweak that we just saw, but it also includes SU3, and this is related to the color of quarks. It turns out that all of our quarks actually come in three colors. Red, green, and blue is just a cute name for three different things. Has nothing to do with actual physical color. But every single one of them has this additional label, this additional charge of red, green, and blue. And we could analyze this using the maximal torus in SU3, but let's just move on to the representations. Oh, and I also should mention that, of course, everybody that's not a quark or an antiquark, such as electrons and neutrinos, they have no color. So they transform trivially. Under SU3. So here it is. This is the standard model representation, where I've grouped these particles together. These are actually irreps. So I'm inviting you, since I'm saying that an irreducible particle is an irreducible, that an elementary particle is an irreducible representation, I'm inviting you to think of these groupings as actually being their own particle, as being, say, the left-handed lepton or the left-handed quark, because they're unified by the gauge symmetry. But this representation, the representation of the standard model, is still highly reducible. I want to take to get all of my particles in the standard model, I'm going to need to take a direct sum of this column. So it's going to be a sum of a lot of different irreps. And part of the point of grand unified theories is to make it less reducible, to unify different particles into fewer irreps. Any questions?
Go ahead.
Hello.
Yes.
Yeah.
Yeah, Professor Huerta. I may have been, you may have addressed this question, but pardon me if I missed something. So what do you think about the Pati Salam model? The three colors and the lepton number combined into the SU4 instead of SU3? And I think that they did that to address the axial anomaly quite naturally.
Yeah, I'm not enough of a physicist to know how to think about the axial anomaly. But the Pati Salam model is one of the grand unified theories that I'm going to describe. The focus in this talk, again, is really on the representation theory, on how the theory of Lie groups sheds light on these.
Thank you. Yeah.
All right, so let's talk about how to unify this picture. So there are three different grand unified theories that I'm going to tell you about. There's the SU5 grand unified theory due to Georgi and Glashow. And it's all about having two isospins and three colors means you have five things. So the idea becomes that you take a space, C5, with just up, down, red, green, and blue. And C5 is then a representation of SU5 in the obvious way. It just becomes a representation by matrix multiplication. But there's another representation, which is the 32-dimensional exterior algebra of C5, given here. So there's some information here that I realize I forgot to leave out, that I forgot to put in, which is that if we take the direct sum of all of these representations, I'm going to call that the fermions. That's the first generation of all fermions. But we also have antiparticles. So I'm also going to consider the dual of this representation, and that corresponds to the antifermions. And to get really all of the fermions and antifermions into a single representation, I need to sum those together. So the standard model representation for us, ignoring higher generations, ignoring interactions and things like gauge bosons, the standard model representation of matter is the fermions plus the antifermions. And here's an interesting question. What is the dimension of the standard model representation? We could determine it from the information on this table. Would anyone like to help me determine it, or should I just go through the math here? All right, so basically you want to count all of these symbols. This is actually a full basis for this, for F, for this representation. But I'm just going to read off the dimensions here. This is one-dimensional, tensor with two-dimensional, tensor with one-dimensional. And when you're doing the tensor product, the dimensions multiply. So this is two-dimensional. This one is six-dimensional. Here's one. Here's one. So far I have 10. And then this is 3, and this is 3. So that means that F is 16-dimensional. Of course, the dual is the same. And therefore, the standard model representation is 32-dimensional. So this is an unexpected surprise that the dimension of the standard model representation is actually a power of 2, right? 32 is 2 to the 5th. And here, this representation, if you work out its dimension, the dimension of the exterior algebra, turns out to also be 2 to the 5th. It's 32-dimensional. So I wonder how these are related. And in fact, the theorem says that I can embed the standard model group into SU5 in such a way that the standard model representation becomes the 32-dimensional exterior algebra. So all this work of figuring out this table is now something really simple and mathematical, which is getting SU5 to act on the exterior algebra of C5. So that feels like a real simplification. Any questions? The next model I'd like to talk about is called the Pati-Salam model. And the idea of the Pati-Salam model is that we want to simultaneously unify left and right, or at least make them more symmetric. You know, it'd be nice if there were a force that treated the right-handed particles in the same way as the weak force treated the left-handed particles. And we're also going to unify quarks with leptons by adding a fourth color that we will call white. So here, very briefly, is how the Pati-Salam model works. It's defined in terms of the group SU2 times SU2 times SU4. The first SU2 is the usual one, the left-handed one. The second SU2 is the new one, it's the right-handed one that's going to make right-handed particles interact in the same way as left-handed. And SU4, like I said, is going to join our leptons with our quarks. So there are two irreducible representations in the Pati-Salam representation, in the Pati-Salam model. And they just look like this. C2 tensor C, the trivial representation, tensor C4, and C tensor C2 tensor C4. So I'm going to write this group because it's a bit long. I'm going to write it as GPS for Pati Salam. I'm going to write the representation as the sum of those parts, plus the dual, because I need the dual to include the fermions, the antifermions. And I have the following theorem, which just says that this is a grand unified theory, that it consistently extends the standard model, or read another way, that when I break the Pati Salam group down to the standard model group, my Pati Salam representation breaks back down to the standard model representation. And there's one final theory I'd like to talk about very briefly before we come to a close. And there are two ways to get it. This theory is called the spin 10 theory. And I could extend the SU5 theory to get the spin 10 theory, because in general, SUN always fits inside of spin 2n. So in the special case where n equals 5, SU2 fits inside of spin 10, and their representations are compatible already. This is the same kind of square as on the previous theorems. So it just says that if I break spin 10 down to SU5, then I break this representation down to the one for SU5. But I can also extend the Pati Salam model. And I may not be so, oh my God. Yeah, there's something I didn't explain here. I'm really sorry about this. This group, I originally prepared this slide for an audience of mathematicians. This group is the same thing as the Pati Salam group. It just looks really different, but they are isomorphic groups. So in this way, we have the SU5 theory extending the standard model, and the Pati Salam theory extending the standard model. And we also have the spin 10 theory extending both of them. Both extends the standard model in two different ways. It extends the standard model via SU5 or via Pati Salam. And one could wonder if these are the same. And in fact, they are the same. They all fit together into a cube, which says that if I break spin 10 down to the Pati Salam model and then back to the standard model, I get the standard model representation. Or if I break it down through SU5 and then down to the standard model, I get the standard model representation. And that's what I wanted to show you about grand unified theories, that there are several nice grand unified theories. They all extend the standard model, and they do so in a kind of consistent way. So thank you very much.
Thank you very much, John, for such a very clear talk. Does anybody else have any more questions? We might have exhausted the questions during the talk. Oh, here we go. Samarth, go ahead. Oh, you.
Yeah. Hey, John. Great
Hi.
talk, and I think this is a really interesting model. I guess my question really is, I guess, which of these models do you prefer working with so far? And if not, I guess, how do you see this model of models growing into the future?
So I really work more on pure mathematics and these days, and therefore I don't work on these kinds of models. I thought that this idea, and in particular the paper that I'm taking these results from, had some interesting thoughts about symmetry breaking, about how to break a spin 10 model down to the standard model. And I think that might be, if there's a contribution to physics, it's probably that. Like, you could think of, like, as you can see right here, I didn't explain, I did a really bad job explaining why this is the Pati Salam group. I didn't explain it at all, actually. But this is the Pati Salam group. And so you can see that breaking down to Pati Salam is really splitting 10 into 4 plus 6. Doing that choice. And then there's a similarly nice description for breaking the Pati Salam model down to the standard model that I'm not remembering at the moment. But if there's a contribution to physics, I think it's probably that.
Okay, so Howard's got a question. Go ahead.
Yes, this is just maybe a sort of technical confusion on my part, or maybe it's even related to the Pati Salam business. But in the Pati Salam model, I think you had there might have been 6 things that I was a little bit confused. Oh, it's on the other side of this page.
Do you want me to go back to some other slide?
Yeah, I think you had
Sure.
like U and D and the colors all together.
That's right. So the Pati Salam model, let's just go back to this table.
Yeah.
So the Pati Salam model is supposed to unify, it's supposed to treat left and right symmetrically.
Yeah, okay, that
They're
makes
not
sense.
unified, but they're treated symmetrically. And it's supposed to unify leptons with quarks. So leptons become a 4th color.
Yeah, that wasn't what confused me. Somehow it was where you had the colors themselves and the up and down all as part of one thing. And I just thought I had written down, but I guess so. Maybe it's on a different page. It could it have been in SU5? I don't think so.
Oh, right. Yes, that's right. So like this one.
Yeah. Well, yeah. So I just somehow wondered, maybe that's it. And this, I think, will help me. I mean, red, green, and blue used to be colors that U and D could come in.
That's right.
That gave, I guess, 6 dimensions, or 6 eigenspaces anyway.
Yes.
But now the red, green, and blue have become things and the up and down have become things themselves. How can I understand that physically?
Right. So this is a very good question. So you should think of things like, you should think of combinations like R and G as being something like anti-blue. Because remember, we need to include the duals also. So there's going to be a red, anti-red, anti-green. Those are the elements of the dual.
Yeah.
So this is anti-blue, and you should think of U as being the obvious thing, as being an up. Sorry, U is isospin up. So this is a bit confusing. U is isospin up. If I just take a U, say like I have some guy in here that's just called U. Right, so these tensors are just length 1, so that's where like things like U will live. Then there's an isospin up particle that has no color. So which particle would that be?
I'm not sure.
So there's so an isospin up particle that's neutral for color is actually the neutrino. And an isospin down particle, its neutral for color, is something like the electron. I think it might have ended up being the anti-electron, the positron, if you work this out. So I'm not quite sure if it's the neutrino or the anti-neutrino or the electron or the positron, but it's going to be those. And that's kind of how this particular game works. You can think of this, you could think of the elements here as being, so they're all wedges of these vectors, and there are no repeated vectors.
Yeah.
So they're like a binary code, right? You can identify an element as 0, 0, 1, 1, 1, and that's going to correspond to like R wedge G wedge B, and no U and D. So R wedge B wedge G is some combination that's neutral under colors and neutral under isospin.
Okay, thanks. Yeah, this is making more sense. So
Okay, good. I'm sorry I can't
no. I of course
unwrap it
read the
fully.
paper and
Sure.
yeah. But yeah, so up and down are actually like all those 5 things actually are properties. I was thinking of up and down
Yeah.
as quarks, and that's not right there. It's isospin eigenvalue or something like that.
That's right. This is U and D are the isospin eigenstates, and the RGB are the color eigenstates. And if you combine these things in the right way, you really can get every particle.
Okay, that makes a lot more sense. Thanks very much.
Sure.
Yeah, that was a really nice talk also, by the way.
Oh, thanks very much.
Hey, Yannis.
So the proofs of all these theorems, does it go down to just a matrix multiplication and exponentials of matrices?
Yeah, it's really, so the proofs of the proofs of this theorem, for example. Yeah, this is just linear algebra, basically linear algebra with a little group theory.
It sounds more exotic than that, but
it sounds more exotic because I'm putting it in terms of all of this great physics that physicists discovered last century, but in terms of the mathematical tools that you need, it's not that exotic. That was why we wrote this paper, to explain particle physics to mathematicians.
And the other thing I didn't understand is, why do you call it a torus? Like how does the geometry of the torus appear?
Oh, I just call it so the torus is just because it's a so the torus you see is, I choose the subgroup of SU2 that's generated by the isospin direction, and I already have a U1, so I have a U1 times U1 group, and so that's
so basically it's a circle that is rotated around the circle
times a circle, exactly. So it's a torus.
All right,
yeah.
right.
Okay,
Good questions.
Wing has a question.
Yeah.
Go ahead. Yeah, so I'm just a simple comment. It's not really something important. I think the two theories are different in the organizations in the particles. Because the SU5, we have 15 particles in the standard model. We can organize into the 5-dimensional representation, the 10-dimensional representation. But the stereo neutrino, right-handed neutrino, is not there. So maybe we have to put that in the singlet one. But in the Pati Salam, Pati Salam is natural. The Pati Salam, you have 8 plus 8, that's 16. So the right-handed neutrino must be there.
Yes. So in this presentation, you raise a good point. In this presentation of the SU5 model, in order to make the representation be as simple as possible, I assume that we have both a right-handed neutrino and a left-handed antineutrino. So like, and these live in this part, right-handed neutrino, and I may be violating the conventions that we laid out in our paper, so it may be the other way, but both of these are trivial. So they're a bit of a strange thing to put in your theory, because being trivial under the gauge group means that you don't interact at all. But yes, there are other theories here, such as spin 10 or Pati Salam, where these are interacting. Here, I just put them in because I wanted to write this exterior algebra. And without these powers, I don't get the whole exterior algebra.
So I think that in the spin 10 theory, I think that the two approach, SU5 and Pati Salam, seem to be complementary. Because in the Pati Salam, the right-handed neutrino must be there, must be in the, you have two representation, right? Each of them 8-dimensional, so therefore you have 16, so it must be there. But we know that the quantum number, of that to be 0, the high spin is 0, iso spin 0, everything 0. So it does not really couple with the gauge field or anything. So this kind of strange, but in this view, the one you're showing here, SU5 here, that because the lambda 0, I mean the first and the last element you put there, even though they look trivial, but this might explain why they are trivial in Pati Salam. You see what I mean? I mean this one, because Pati Salam require them to exist, but we don't know why they don't. I mean, it cannot explain why they have the 0 quantum number. But in this view, SU5 seem to be confirmed that it has to be 0 quantum number. So the two views are complementary.
That's an interesting way of looking at it, I mean, that was sort of the punchline of our paper, is that you can understand the standard model in some ways. In some ways, a good way to understand the standard model is to think of it as being broken down from spin 10 in these two different ways. We actually proved that if you take the Pati Salam subgroup of spin 10 and you take the SU5 subgroup of spin 10 and intersect them, you get the standard model subgroup. You get the standard model gauge group. So that sounds a little bit like what you're saying, that they're complementary.
Thank you. Because usually for a long time, my own way is kind of like more, into the Pati Salam, because I think it's more natural. But from your talk here, I think that I should not overlook the SU5 either, because it's either, add some value there. Thank you.
Sure.
Hey, Francis has a question.
Hi, Francis.
Okay, yes. Thank you, Prof, for your presentation. Yes, I have a little concern with the use of the word spin. In the particles, we still use spins, like the spin half, the spin 1, and we like the iso spins. And in the structure that you just showed for the Pati Salam 2, we still use spin 10. Are you considering the spin as the spin group that is in geometry, or the spin Lie structure in particles?
So I am considering the spin group in geometry, and the reason that it's called the spin group does have to do with this history of being related to spin for particles.
Okay.
But the spin in the spin 10 is not really related to particle spin.
Yes, because I have a little concern because of the structure of the spin half, which is an SU2 group, which is a compact. The Lie structure is the SU2. And when we take the spin group in mathematics, which is spin 2, the spin 2 in mass is rather the SU2. But in physics, we only have a spin 2 to be a graviton, which is not an SU2. So sometimes I'm a little concerned with the language of geometry and that of spin particles. Yes.
Right. And yes, and I can understand why these kinds of things would be concerning or confusing. So one correction is that it's actually spin 3 that people think about in, say, quantum mechanics, because it concerns 3-dimensional rotation.
Yes.
And that is the same, then that happens to be the same thing as SU2.
Yes, absolutely.
And yeah, I'm not entirely sure what to say. I mean, I think that physicists in the last century, they kind of they at first they didn't know representation theory. So any interesting representation of SU2, they just called it spin.
Yes.
But now, you can also think about other things.
And with the usage of the spin term, if we consider the spin term, then with the structure, I noticed we have a lot of the C. You use the C5, C3. Are you considering that in terms of the Clifford algebra or the stereo structure, which is in geometry? Because if we are considering that in the terms of elementary particles, won't it be appropriate to use both as you use the stereo? Won't it also be appropriate to use the interior structuring too?
So I do have, of course, C5 and C3, these are just complex vector spaces.
Yes.
And they're not really related to Clifford algebras, but there is a relationship to Clifford algebras, and I went past it really quickly on this slide right here. So the way that this construction works, everything about the spin group, spin groups are always related to Clifford algebras.
Yes.
And so the fact that it has this representation is actually constructed in terms of the Clifford algebra operations. So you can think of like wedging and interior producting as defining Clifford algebra operations that give you this action of spin 2n on this exterior algebra.
Yes.
And there's there's a way that these act, and you can find a map that makes them all compatible. So there is the Clifford algebra here. There's always Clifford algebras when you see spin groups, but I didn't need to talk about it today.
Okay, and for the last question I would like to ask, with this structure that we have here, so the gauge group, which is the SU5, is it a boson or a fermion?
The gauge group is an SU5. What do you mean? So there's
because when we take for instance, we take SU2s, which is a spin half. We know a spin half is a fermion. So the gauge group, the correspondence, which is you have a spin 10. Would you consider the gauge group, which is SU5, to be a boson or a fermion?
So I would consider it's hard to make sense of the question for gauge groups. You can ask about the gauge bosons, which are related to the gauge group. They're the Lie algebra of the gauge group.
Yes.
And they're always bosons. They're as stated in the name. So I would think that SU5 is really bosonic. The way that I structured this talk is like all of the representations I talked about were representations of fermions. But I didn't explain, I didn't say anything about the relationship between spin and statistics, and that's not visible at all here, because that has to do with relativistic quantum field theory, and I'm not doing anything that fancy.
Okay. Okay. Thank you very much.
You're welcome.
Zerab, just let me unmute you here 1 second. Okay. Go ahead, Zerab. We might have lost him. Okay, I think so. All right. So if we, oh, here we've got Howard's got a question as well too. Go ahead, Howard.
It's a quick and easy one. I had a question about the page with the Gelman-Nishijima formula.
Sure.
So I was just that either I'm not understanding something or maybe there was a typo.
Definitely both things could happen.
And oh yeah. Yeah. So I was just wondering, should that be an I3 or?
Yes, that should be an I3.
Okay,
good.
That's
definitely
that's not important, but if I was confused, that's important to me to unconfuse. So good. Thanks again. That was really cool.
You're welcome. My pleasure.
Okay, so give Zerab one more chance, see if his.
Okay, can you hear me?
Yes, we can hear you. Go ahead.
Okay, when you unify quarks and leptons, baryon number becomes violated. So proton can decay.
Absolutely.
Can, for example, SU5 give some natural prediction for proton lifetime and how it corresponds to experimental limit?
So I'm not a particle physicist, and I'm not in particular a phenomenologist. Those are the kinds of people who specialize in making predictions like that. I know that they did make these predictions for SU5. I think they made it for all of the theories we've discussed. And at least SU5 in its simplest form has been ruled out because the proton is too stable for SU5, as we've stated it here, to be the correct grand unified theory. I believe that might not be true if you add some supersymmetry. I think that some version of supersymmetric SU5 might still be a contender to be true, but I'm not up to date on this.
Okay, thank you.
You're welcome.
Well, now might be a good time to close things off. Thank you so much, John, for such a very clear talk. Really,
thanks.
Yeah, I really appreciate that. Thank you. Let's see here. So I should mention that our next talk is scheduled in 3 weeks on the 24th of April, 7 p.m. Berlin time. So that's 1 hour later than usual. We've got John Bias, backed by popular demand. John will be speaking for us on part 2 of what he and others call the tenfold way. Thank you sincerely again, John, for giving such a clear talk and for fielding so many questions.
Sure.
And thank you everybody for showing up and for your questions. And we look forward to seeing you again next time.
All right. Thanks for having me, Cohl. It was a pleasure.